Okay, let's do a little bit of review. So where are we? We're starting a important section, which is magnetism, and we understand the concept of the magnetic field. And magnetic field is denoted by the letter B. It's a vector. It's got a strength and a direction, just like electric field or gravitational field or any other field. And we understand that if a charge moves through a magnetic field, that a magnetic field does not exert a force on a stationary charge, but if a charge moves through a magnetic field, then the magnetic field exerts a force on the charge, which is equal to the charge times the velocity cross B. We have to understand what the cross product is, and that this is in magnitude it's QVB sine theta, where theta is the angle between the V and the B vector. So the V vector and the B vector, we got to put them head to tail. This would be theta. Not head to tail, not head to tail, not head to tail. We've got to put them tail to tail when we were talking about the angle between two vectors. That's theta. And so the cross product has a magnitude of QVB. In other words, the magnitude of the vector FB is QVB sine theta, and the direction is given by the right-hand rule. The right-hand rule is where you put your fingers in the direction of the velocity, you rotate them towards B. You put your fingers in the direction of the first one. You put your fingers in the direction of the first vector, and you cross them or rotate them towards the second vector, and your thumb points towards the direction of the force. So in this case, when this charged particle enters the magnetic field from the left to the right, it initially feels a force out of the page towards you. And that means it's going to start rotating towards you, and so now the particle is going to come out of the page. And that is if Q is a positive particle. If Q is a negative particle, it's going to be the opposite of that, because in this equation here, the Q would be a negative, so the direction would be negative of whatever V cross B gives you. Okay, so direction given by the right-hand rule. Okay, so we understand this, and that also says that if charged particles move in constant fields, they must go in circles. And we saw how if something's going in a circle and the force that moves it in the circle is called the centripetal force, then that centripetal force is also equal to mv squared over r, and so we can figure out the radius of the circle that the particle will go in, etc. So that's a review of that. Then we extended that to currents. A moving charge is just a current. So then we were able to show that implied that if you have a current carrying wire, a straight current carrying wire in any kind of magnetic field, or in a constant magnetic field. Sorry, if you have a straight current carrying wire in a constant magnetic field, the magnetic force on that wire is IL cross B, where L is the length of the wire, and L has a direction, which is in the direction of the current. I is the current in the wire, B is the strength of the magnetic field. And we're able to figure out the forces on current carrying wires that way. And again, the cross product, in this case, the cross product, remember the current is the direction that a positive charge would move. So in this case, the magnetic force is in the direction of L cross B, and L cross B in the picture that I've drawn here is out of the page towards you. That just means that the wire feels a force out of the page. It doesn't mean the wire is necessarily going anywhere if the wire is fixed in place, but it does feel a force out of the page. The wire as a whole feels that force. It's not letting me pause. I think my pencil stopped working. Hold on a second. So as a continued review, I'll do another example of this. But then we want to talk about what if the magnetic field is not constant, or what if it's not a straight wire. But first, let's do an example of a constant field in a straight wire. Okay, so let's do a problem. Let's say that we have a high voltage wire from a power company, and it's parallel to the ground, as high voltage wires are, because we generally run them, along highways and through wooded areas, etc., parallel to the ground from the power company to wherever we're bringing power. What is the minimum and maximum force on it at the equator and at the geographic North Pole due to, and this is what I didn't write down, the magnetic field of the Earth? The magnetic field of the Earth is 3 times 10 to the minus 5 Teslas north at the equator. It points in the north direction at the equator. And over here on the left, I have a picture of a kind of a picture of an Earth and a single field line. Then that field points at the equator. It just points north along the parallel to the surface of the Earth. And at the equator, the magnetic field is twice as large, 6 times 10 to the minus 5th Tesla, and it points down towards the ground at the geographic North Pole. Remember, that is the magnetic South Pole, the top of the Earth. Geographic North equals magnetic South. And so in order to answer this question, I need to give you the current in the high voltage wire. Let's just say that a high voltage wire carries, let me look it up actually. Just tried looking up the current of a high voltage power line, and actually it's a little bit difficult to figure it out, but it seems to run, maybe it's about 50 amps, seems reasonable for a single wire. And so I'd like to know what's the effect of the Earth's magnetic field on these wires that are strung across our Earth. And that's what we're going to calculate here. The other thing I want to do is to discuss the direction of the forces at these two locations. And the direction of the force is going to depend on the actual direction of the wire. And the wire could go, north to south, east to west, or anything in between. But let's discuss the direction. So let's start with first at the equator. So from the previous page, at the equator, the magnetic field is 3 times 10 to the minus 5 Tesla north, and the current carrying wire carries a current of 50 amps, and that can be in any direction. So then we want to think about what direction would it be so that there's a minimum magnetic force, and what direction would there be a maximum magnetic force. So if FB is IL cross B, and we're assuming the magnetic field is approximately constant and the wire is approximately straight in order to use this formula. We will discuss if it's not next. The question is when is this a maximum, when is it a minimum? Well, we can figure that out by looking at the magnitude of the force, which is ILB sine theta, and that's going to be a maximum or minimum depending on the angle between the wire, L, and the magnetic field, B. And we know that sine theta is a maximum is equal to 1 if theta is equal to 90 degrees. And sine theta is a minimum, 0, if theta equals 0 degrees. Therefore, FB is a max when what? When the wire, the current carrying wire runs perpendicular or 90 degrees to the magnetic field. The magnetic field points north, so the wire has to point east or west, right? That's perpendicular. It's not going to be up or down because the wires run parallel to the ground, so the current must run east or west. Okay. So I just wrote that down. When the current carrying wire, the direction of L is east or west, perpendicular to or 90 degrees to the magnetic field. And FB is a minimum. Whoops, my pen keeps on stopping working. I'm having some real technical difficulties. Okay, and FB is a minimum. Whoops, FB is a minimum if theta is 0 degrees, so that means the wire runs north to south. Or south to north, right? So L points north or points south. So if the wire runs north to south along a north-south highway or south to north along the same highway, then FB is a minimum. So what are those maximum and minimum values? So FB max is ILB sine 90 degrees, which is 50 amps, times L times B, which is 3 times 10 to the minus 5 Tesla, times 1 for sine of 90. Now, you might say, well, what am I supposed to use for L? Well, it doesn't actually really make sense with a wire. These are basically, we're treating them like infinitely long wires. Or at least they go miles and miles and miles and miles. And we can figure out the net force. But what really matters is what's the force in a given area, right? And what's the force at a given location? And so we could say, what's the force on a single meter of wire? Or we could say, what's the force on a single meter of wire? Or we could just talk about the force per unit length. So therefore, right, the force per unit length, FB max over L, that's force per meter. If we're talking about, that's newtons per meter. If we're talking about MKS units, right? So it's the force on a meter of wire is going to be 50 amps times 3 times 10 to the minus 5th Tesla times 1 meter if you want. Gives us 1.5 times 10 to the minus 3 newtons per meter. So there's a force of 1.5 times 10 to the minus 9 to the minus 3 newtons per each meter. What's the FB minimum? Hopefully you can see that FB minimum is 0. If we run these wires north to south instead of east to west, then they're going to have a magnitude of force of 0 because sine theta is going to be 0. The direction for the maximum force, the direction depends on whether the current runs east or west. But if the current runs from west to east in the picture that I've shown over here, then the current goes to your right, the magnetic field goes north, the magnetic field goes up, and the cross product, think about it before I tell you, put your fingers in the direction of I to the right, and you curl them, right hand, use your right hand, curl them towards B, which is north, and then the direction of your thumb is up out of the page. Now think about it, we're looking down on the surface of the earth right now. You're looking down on the surface of the earth, so the direction of the force, the magnetic force on this current carrying wire that runs from west to east is upwards away from the surface of the earth. And therefore, if the current ran east to west, if the current ran in the opposite direction, then the force would be down towards the surface of the earth. But it's a small force, 1.5 times 10 to the minus 3 newtons per meter, and so probably not a terribly noticeable force. It's not an unmeasurable force, but it's not a noticeable force. And the direction, if we run north to south, there is no direction. There is no direction associated with a force of 0 newtons. So at the geographic North Pole, remember the field points down towards the ground, so the field points perpendicular to the north, south, east, west. What do you call that? The compass rose? And if the power lines are parallel to the ground, right? It doesn't matter whether the power lines run, which direction they run, they're always going to be perpendicular to the field. So in that case, at the North Pole, the field is always going to be the same. There is no minimum or maximum, right? The magnetic field, ILB, the magnitude of the magnetic field, ILB sine theta, theta is always 90 degrees at the North Pole because the power lines are running parallel to the ground and the magnetic field is running perpendicular to the ground. So the magnitude of the force, therefore the magnitude of the force that you get at the North Pole is 50 amps times L times, now we've got 6 times 10 to the minus 5 Tesla times the sine of 90 degrees. We get 3 times 10 to the minus 3 newtons per meter. So you get the force is twice as large, 3 times 10 to the minus 3 newtons per meter, and that is not dependent on the orientation of the power line. Again, in the picture shown, the power line is the red going left or right or in or out, whatever, it's parallel to the ground, and the magnetic field is going down towards the ground. So in that case, the direction of the direction of the force, is always going to be perpendicular to the magnetic, right? Because it's, again, I'm going to write it yet again. IL cross B. It's always perpendicular to the direction of the current and the direction of the magnetic field. So since the magnetic field points down towards the ground, depending on the orientation of the wire, the direction is always going to be parallel to the ground, but it's always going to be perpendicular to the wire. And so, we could say, anyway, you can't even talk about east, west, north, south because we're at the North Pole. But anyway, so the direction is always going to be parallel to the ground, perpendicular to the wire. But whether it's left or right depends on which direction the current runs. Okay, so that's the full answer to the original question.